Good evening, everyone. Thank you for coming along for this EPECentre Seminar, which is related to one of our research projects and dealing with introduction of photovoltaic cells and photovoltaic generation and electric vehicles and the impact on the grid. The presentation will be undertaken by two presenters, Dr. Sharee McNab, who is a research engineer with EPECentre, and our PhD student, Euan, McGill. Just a few ground rules. We have a number of participants online. So we'll take the questions at the end to help with the progress of the presentation. There will be questions coming through online, and Isabel will have them all with her. When you are asking a question, please could the speaker repeat the question for those online so that they can hear? Start. Thank you.
Okay. Thanks everyone, and thanks for the introduction, Radhnya. So this project, as Radhnya said, is a green grid project that started back in 2012. It's something I presented a month ago at the Asset Management Forum, so if you were there, you might find this quite familiar. So what we're going to talk about is two separate things: photovoltaic generation, so generating electricity, but also electric vehicles, a load on our distribution networks. And we've put those together because there's a lot of similarities, even though they are the opposite, generation and load. And we're really concentrating on the effects on the distribution network. What?
Start again. I know.
So to give you an outline of my talk, first of all, give you a little bit of a background about the uptake of distributed technologies. Then we'll talk about some work we've done on looking at photovoltaic hosting capacity and introduce you to a tool that we've developed here at the EPECentre. Then we'll move on to a comparison, what the similarities and differences are with modelling PV compared to EV. And Euan is going to present some of his research work on modelling electric vehicles and their impact on hosting capacity. So there's a few acronyms that I might forget myself, so I'm just declaring them now. DG is distributed generation, so that's when you have generation that's close to your load. PV for photovoltaics, so solar panels, and I'm sure you're all familiar with EVs. So distributed technology uptake has been increasing quite steadily. When this project started back in 2012, there was less than 2 megawatts of solar installed, and this is predominantly in the distribution network, so it's in mostly residential, although commercial properties, commercial entities are finding it increasingly more attractive too. But last month we broke the 100 megawatt barrier, and after quite a sort of exponential growth here as panel prices decline quite sharply, we've kind of been on this linear track. So you can see from electric vehicle uptake, it's also had a similar kind of exponential growth here. It started more recently in 2014. We're at about 15,000 registered vehicles today, but that's estimated to be a lot higher and perhaps even outstrip the amount of PV going from what it looks like today. So this is a more recent addition that electricity distribution businesses are becoming aware of and increasingly want to understand what effect that's going to have on their businesses. Now, why do we care about EVs? Isn't it just another load? Well, EVs happen to be a very big load, so they do have quite an impact. Excuse me. So from looking at photovoltaics worldwide, the International Energy Agency released a report last year showing we've actually got about 500 gigawatts of PV worldwide now, with countries like China leading the charge. But if you look on a per capita basis by country, actually Germany has the most. This is because they've had a lot of incentives to install PV on their roofs, Australia as well. But this doesn't tell the whole story, and what's relevant, particularly for distribution businesses, is what's happening at the local level. So if we compare New Zealand, New Zealand's about 21 watts per capita, a pretty paltry amount. But what's really of interest is actually in areas we have clusters of the PV, and when we have a cluster of PV there, we're going to have the same impacts that they're seeing in other parts of the world. It's just a little thought experiment. What would happen if we got to 500 watts per capita? Well, that's 2.5 gigawatts of generation, emitting the capacity factor, which is quite low for solar. That's over a quarter of our generation currently for whole New Zealand. So, you know, there is the potential to be quite significant, although we don't know if it'll get to that level. So what is the impact on distribution networks? Now, we described it in terms of congestion. If you have a lot of PV localised on a network, we can get issues such as network voltage limits being exceeded, which can have issues for your energy security. Another issue we can have is equipment ratings can be exceeded, both for transformers and cables. And what is often talked about is this reverse power flow. We're used to distribution networks feeding out the power to the edge. Now it can be the edge feeding it in at times of high generation, which is typically the middle of the day, and low loads, which are often coincident. So the graph here on the right, this shows what's happening to voltages. I've got the distance from the transformer along the x-axis, so we have our transformer here. This is a per unit voltage, so it's just normalising the voltage, and we've got in purple two main feeders, and each of those black dots is an electricity connection, so it might be somebody's home or business. The red dots represent where we've modelled PV, and as you can see, this voltage is steadily increasing, but if you look at this one, it's dramatically rising. So we've got a lot more PV at the edge generating here, and if distribution businesses, they're really at the coalface of this, they need to control what's happening to these voltages, and it's in this situation, you can see this feeder has exceeded the regulatory limit that they're required to maintain these voltages in. Now, if we just turn to EVs, EVs is similar yet opposite. So I think electricity distributions are more used to the loads and the voltages dropping. So what you actually have is if you have a whole lot of EVs charging, we'll neglect thinking about vehicle to grid at the moment, what we're seeing is that the voltages can drop quite sharply. And so if you put it all together, it doesn't actually cancel out, unfortunately, because the times when we've got high generation does not usually coincide with high loads. So actually what distribution businesses are worried about is these extremes, so the very high voltages and the very low, so you're getting an increase in spread. So let's now look at hosting capacity for photovoltaic systems, and then I'll introduce this DGHost tool. So there was a lot of work when initially into this project. We were very lucky to be able to get some full network information from some electricity distribution businesses in New Zealand, and this involved getting how all the conductors connected to the transformer and where all the ICPs were. And what we did was model a whole lot of scenarios for increasing levels of PV on these networks. And this included looking at different points where the PVs were found. So typically if you have PV at the end of the network, you have some more issues with voltage, less so close to the transformer. So we did a whole lot of simulations, came up with what the hosting capacity were for these different networks, and these distribution businesses were very happy. We've had a network analysis group that we've been working in, which is working with different people in the industry, electricity distribution businesses, inverter manufacturers, and the electricity authority, people interested in what's happening. And the feedback we got was a lot of the electricity distribution businesses can't actually make use of these techniques because they don't have full network information. So they've maybe got incomplete records or paper-based. And so the option to do this, the ideal situation where you model everything, is not available. So their question to us was, well, what can we do in this situation? So this is when an approximate method was come up with. So this was able to use simple inputs that the EDBs did have about their network and leverage the full modelling that was done by taking that as a, using it as a large representative database. This is what I'll talk about now. So DGHost is an approximation method. It's using statistics to make an estimate for what the hosting capacity is for a network. So what do I mean by hosting capacity? Well, that's the maximum export that your solar panel or your PV can export into the grid. So it's considering on a per network basis. And that's before we have issues with congestion, such as the high voltages or current limits being exceeded. So the idea was to estimate hosting capacity by looking at your network of interest, trying to find the networks most similar within this database. And we were lucky enough to have about 20,000 networks. But when you considered all the different scenarios of increasing levels of DG PV in your networks, and also all the different possible combinations of where those PV can lie, ended up being into millions of results, hosting capacity results. So then the question is, well, how do we identify a similar network? And for that, we had to choose some predictive variables that would define the sort of network it was. And the hypothesis is if you've got a similar network parameters, you're going to have similar hosting capacities. So a number of different predictive variables were optimized, and the idea was to get them as independent as possible and also easily determined by EDBs to make it useful. We ended up with 4 different predictive variables, and then we used a k-nearest neighbour regression technique. And I'll just explain that by using a picture. If we consider the cross as our network, and we can define it by having these, if you look at the x and the y-axis, they're variables, our predictive variables, they have a certain value for those. What we can do is look at the nearest neighbours, so you do an Euclidean distance. This is in 2 dimensions. In fact, because we've got 4 predictive variables, it's actually happening in 4 dimensions. So we're trying to find which are the closest networks. There's also some statistics which weights more heavily the networks that are closer than the ones further away. And then each of these blue dots happens to be a distribution for these networks too, because as I explained, if a network's got more than one ICP, there's a number of combinations that you can have with where you have your DG, your photovoltaics. So when I say DG, I'm really referring to photovoltaics because that's the most common distributed generation we have. So the predictive variables then became the inputs for DGHost. This has been developed into an online tool which is available, and this is the input screen. And you can see these are our predictive variables, the transformer rating, the number of connections, like how many houses or businesses you've got connecting in, the maximum feeder impedance, and from feedback we've got from people from the EDBs, that's the more difficult one to determine because sometimes it's not so easy to work out depending how well your network is known. The 4th predictive variable is here PV penetration. So what do I mean by that? Well, that's the number of PV installations you've got on your network. And so what we don't want to do is just feed in the current PV penetration. This is really as a forecast for how many PV are we likely to get in this network in some defined future. Because we want to be able to look at the hosting capacity in the future when different people will apply to connect DG to make sure there's enough hosting capacity to go around. So we also look at different network types, whether it's a 3-phase network, single-phase network. Reduced neutrals just refers to overhead lines in a certain generation were often rolled out with their neutral conductor being smaller, and that has an impact on your hosting capacity. So just to go through an example, this is a GIS of an EDBs network who we were talking to about hosting capacities. If you look at the black circle, that's where the transformer is. We've got the blue and green and yellow are different feeders that feed into that transformer. There's actually some other transformers over here. So it's very easy to look at the inputs and determine what the transformer rating is, the number of connections, and maximum and feeder impedance. The question about PV penetration, well, this just shows an example. In this case, we've got 7 of the 31 connections, which are the spurs coming out here, have got DG installed. And that gives us a PV penetration of 22.6. Because this is a difficult parameter to characterise, we've actually produced results which have give you the option of putting a number of penetrations, so you can look at the sensitivity as you increase your number of PV installations. So this just shows you a very small part of the results for this one penetration level. It gives the hosting capacity for the network of interest. I've got this two values, a conservative and the median. Now, because we're dealing with distributions and when we find our hosting capacity for our network of interest, this is also a distribution of hosting capacities. So what we do is take this 25th percentile. That means that for a hosting capacity of 5,400 watts, there's actually 75% of that distribution has a hosting capacity higher than that. If you're feeling less conservative and you're happier that you don't need to be that conservative, you can use the median result. So half of the network results will have hosting capacity higher than 5,100. So I've just shown two penetrations here, and the tool you show 4. So this gives you an idea of basically the strength of that network to host PV. So some further analysis was also undertaken, and that's recent PV inverters are coming out with some additional features which are helping support the grid. These are defined in the recent standard, Australia New Zealand 4777 standard. So these grid supporting features have the PV inverter able to operate autonomously. In particular, I'm referring to the voltage response mode. So the inverter is monitoring its voltage output. So when the case that we have a lot of generation and maybe low load, the voltage is starting to rise. If it gets to some critical set point, it will change the power factor and start absorbing some reactive power. And if you look at this graph here, this comes from the connection guideline. We've got the voltage here along the x-axis. This is whether it's how much reactive power, so 0, it's just all real. So if you look at this, we're meant to be at 230 volts. As you increase to the set point here, you can start to get a gradual linear increase in the amount of reactive power that's absorbed. And this is going to act to reduce your voltage and bring you back, hopefully, out of the danger zone. There's also other response modes, volt watt, for example, but we've just focused on this volt var, and I'll show you the results we've done the simulations for the power flows incorporating this effect. So I've already showed you the initial results for just real power when we start to add, say, 30% of the reactive power of the inverter. You can see that looking just at the conservative hosting capacity, it goes from 5,400 up to 6,900. So you're getting an increase in how much PV you can put on that network if all the inverters are operating with that mode. And if you increase to 60%, so it's reducing power factors, you've got even higher hosting capacity. So we're at now 8,900, and that's getting to the limit of where you start to exceed the small scale regime for distributed generation. So the DGHost tool provides these hosting capacities. These can be used in a number of different ways. One way is to look at prioritising network reinforcement. Which networks have low hosting capacities. They're going to come into trouble when you've got DG or PV installations. So it can prioritise if you need to, I don't know, go to a larger transformer or reconductor to help with those congestion issues. It's also in discussion at the moment. The Electricity Authority has currently been discussing including some hosting capacities for networks. And part of the application process, so when you install a PV system, you have to put an application into your EDB. There's a fast track system that's defined by the Electricity Industry Participation Code. And that fast track process, part 1A, there's talk about including some hosting capacity so that we can use a sort of traffic-like system to say, if you've either got a low hosting capacity that's not going to cause too much congestion, or not expected to cause a lot of congestion, that can go straight through and do a fast track if some other conditions are met. There's also, that's under discussion at the moment. Okay, so we've been talking a lot about hosting capacity for photovoltaics. EDBs are actually interested in what's happening with EVs as well, and in fact maybe more so, as they see this as increasing at even higher rates than PV. And as I've said, there's a lot of comparison, a lot of parallels, but there are also some important differences which make the analysis a bit more complicated. There's more parameters to consider. So apart from the obvious difference that one's generating and one's a load, location is an important issue for PV modelling. The EDB, electricity distribution business, it knows where the PV is being located on the network because there's a requirement to register this and apply to install this system. For EVs, at the moment, anybody can plug in anywhere. There's no way of knowing where EVs are unless you incentivise registration, perhaps with tariffs, or do some load analysis of smart data. But really, this is not a known, and there's a number of people in the sector trying to call for, particularly if we're starting to use large EV chargers, that they be go through a similar application process to the photovoltaics. Another difference is the energy profile. When we're generating solar energy, the sunshine hours are very well defined. We know when there's lots of generation and when there's not. We've got long historical records. There's a lot more diversity in how people want to charge their vehicles. So there's different frequencies. Do people charge every day, every 2 days? How far do people go? And also how big are their charges. So there's a lot of additional parameters that need to be addressed. There's also the consideration of the correlation. In your low voltage networks, you always have a high degree of correlation with your PV. Typically, your low voltage networks are a very small area. If one panel is seeing sun, the others are too. However, there are small variations with the tilt and orientation, but as a rule, you can make some good assumptions there. However, if you look at EVs, there is the potential for a lot more diversity, which actually is great for EDBs, but there's also a lot of more uncertainty, particularly at the moment, about how EV owners are going to charge. So modelling that is more of a challenge. And that is a great place to hand over to Euan McGill, who's been doing a lot of work in this area, modelling EVs and what affects the hosting capacities of their networks. I haven't been using this. Yeah.
Try to keep this in second.
You go.
Hi everyone. So as Sharee touched on there are a number of considerations which need to be taken into account in modelling electric vehicles. Today I'm going to discuss a number of these and how they've been incorporated into some initial EV impact studies. Those in particular, which I'm going to talk about today, are charger rating, charging strategy, range anxiety, EV availability, and EV energy requirements. Okay, so EV charger rating. EV charger ratings can be broadly classified as either slow, medium, or fast, the ratings for which can be seen here. At present, the dominant charging technologies have ratings around 2 and 4 kilowatts. However, it's anticipated that in the future, that dedicated fast chargers in the region of 7 kilowatts will become increasingly common. These have the potential to double the peak load of individual households. Whilst these offer benefits for EV owners in terms of charging duration, undiversified charging can cause undesirable peak loads and distribution networks. Charging strategy describes the way in which EV load is managed. The simplest of which is the passive approach, where EVs are simply plugged in upon arrival home each night. Delayed charging can also be implemented with charging triggered by either, sorry, can you all hear me? No worries. Delayed charging can also be implemented with charging triggered by either a timer or starting overnight at the time required to be full upon departure the following morning. Perhaps looking a little further into the future, coordinated charging of multiple EVs by a third party may be able to provide some benefits to networks. Range anxiety is a word often heard when discussing electric vehicles. It essentially describes a EV owner's tendency to charge. For example, will EV owners charge every night independent of their state of charge on arrival? Or will EV owners only charge when their state of charge on arrival is insufficient to meet their journey needs the following day? Reducing range anxiety can provide benefits for distribution networks. However, this is at the cost of reducing flexibility for unplanned journeys for EV owners. Okay, so EV availability. I guess, of course, it would be beneficial for EVs to charge during the day when network loading is typically low. However, during the day, EVs are typically away from home and thus not available for charging. The overnight period is the most suitable window for EV charging, although the question remains, at what time do EVs arrive home each night? Equally, at what time do they depart the following morning? And also, how correlated are EV arrival and departure times among EV owners? And finally, what are the energy requirements for EV charging? EV battery capacities vary between makes and models. I believe, although I could be wrong, there's 2 capacities available within this Leaf at present, which are 24 and 30 kilowatt hours, and that future capacities of 40 and 62 kilowatt hours are expected. The question is, how far are EVs typically driven each day, and thus what would be typical values for the arrival state of charge when EVs arrive home each night? Okay, so I'm now going to discuss some initial modelling work which has been carried out, including how each of these aforementioned considerations were taken into account. I don't really have enough time to go into the modelling framework in too much detail, so I'll try and just stick to the essential details. A single residential LV network was modelled, and the topology of it can be seen here. This network was identified from cluster analysis and thus represents, within the data set we have, the most typical residential LV network. It's got 71 connections in total, 68 of which are residential and 3 are commercial. It's got a mixture also of overhead lines and underground cables, and they're indicated by the dashed and non-dashed, I guess, lines on the figure there. Couldn't find the word. Okay, so yeah, a week-long quasi-steady-state load flow simulation was implemented, where non-EV load was modelled using smart meter data. The simulation has a number of stochastic inputs, which include the specific smart meters, which were sampled from the dataset, placement of these smart meters within the LV network, also the placement of electric vehicles within the network, EV arrival times, EV departure times, and also the distances travelled by electric vehicles. A probabilistic approach is implemented, which performs multiple iterations of the week-long load flow simulation and therefore produces statistical results. Work so far has assessed the impact of charging strategy, charger rating, and range anxiety. Okay, so yeah, just a little bit more information on the stochastic inputs. A smart meter dataset of over 2,000 premises was used. Smart meter anonymity means that the locations of those smart meters are not known. Instead, smart meters are sampled at random from the dataset and randomly distributed throughout the LV network, seen here. The distribution of annual energy consumption within the dataset can be seen in the histogram here, demonstrating a variation in property size within the data. Similarly, the placement of EVs can have a significant impact on load flow results, especially at low penetration levels. If you look at the network here, say a low penetration level that constitutes roughly, say, 10 EVs within our total 71 connections here. If I randomly place those EVs, and it so happens that a higher percentage of them are towards the end of these feeders here, then the load flow results are provide slightly more extreme voltages than would be observed if we place those EVs towards the beginning of the feeder. So EV placement was another thing, as another stochastic input to our simulation. EV arrival and departure times are also sampled from a distribution. EV arrival times are sampled from a normal distribution centered around 6 p.m. and this can be seen in the blue here. The distribution's got a standard deviation of 1 hour. Similarly, a normal distribution centered around 8 a.m. is used for EV departure time, and again the standard deviation is 1 hour. These distributions were assumed in the absence of the required survey data. So this is the validity, I guess, of these distributions is an area of ongoing work. And I'm always open to collaborations if anyone in the room or listening online has the required information that I might be missing. Daily distances travelled are sampled from the distribution seen here. This data is taken from the Ministry of Transport and accounts for all light passenger vehicles. So the upper tail of this distribution was clipped to account for the maximum possible range of electric vehicles. Okay, so let's first look at the impact of different charging strategies. Here we're going to consider 3 charging strategies, and these are labelled, I'm sorry if the axis labels here are a little bit small, on arrival, delayed, and by morning. The arrival strategy means that all EVs are simply plugged in and begin charging when they arrive home each night. Delayed means that all EVs are delayed to begin charging at 9 p.m. and by morning means that EVs begin charging at the time of night required to be full on departure the following day, if possible. These charging strategies were chosen because, as far as I'm aware, this capability is available within the majority of EVs which are currently on the market. So what we can see in the load profiles here are the aggregated load profiles, so the LV transformer load profile for 7 consecutive days for Monday through Sunday. So Monday, Tuesday, Wednesday, Thursday, Friday, so on and so on. The blue load profile corresponds to non-EV loads. This is the baseline case. And then the red, yellow, and purple profiles are the additional loads due to EVs at 3 different penetration levels. So 30% in red, 67% in yellow, and 100% in purple. It's probably worth noting at this point as well that all these load profiles assume that the entire EV fleet is using the 2 kilowatt charger. It can be seen that both the delayed and by morning strategies, so the second one, third one, shift electric vehicle load outside of the peak in the conventional, in the non-EV load, sorry. One limitation with the delayed charging strategy is that it reduces natural diversity due to variation in arrival time. So if you imagine we've got 71 EVs in the network and all these guys are living vastly different lives, they're all coming home at different times, so our EVs are getting charged, they're getting plugged in at different times. If they're all responding to a uniform delay trigger of 9 p.m, then we lose all that diversity and all the EVs start charging at 9, which can be so shifting the load to 9 o'clock, if they're all going to start at 9, can sometimes be counterproductive, especially at higher penetration levels. Diversity is maintained with the by-morning strategy due to variation in departure times the following day, but also variations in the arrival state of charge. So we don't see that sudden step with the by-morning strategy. The graph here, didn't turn that on. The graph here shows the probability of 1 or more voltage violations being recorded over the course of the week. The simulation has a temporal resolution of half hour, So this is the probability that one or more half-hour intervals within the week will have a voltage violation, and that's a steady state excursion outside of the statutory limits of plus and minus 6%. So yeah, the simulated week used data from the 16th to the 24th of June, which contained the winter peak for that year. There's a small voltage violation probability even without electric vehicles added. For all charging strategies, that's arrival delayed in morning, we can see that the voltage violation probability increases with penetration level. The by morning strategy consistently provides the best performance. That's the bar indicated in yellow there. And we can also see that delayed charging, so if charging is delayed to 9 PM at night, that provides improved performance against simply charging when you arrive. However, the extent to which this provides an improvement decreases as the penetration level increases. Again, it's important to note that this corresponds to the 2 kilowatt charger. Sweet. Moving on, let's now look at the impact of charger rating. Here we're going to consider 2 and 4 kilowatt chargers corresponding to the slow and medium classifications that were discussed previously. Again, shown here are the weekly transformer load profiles for 7 consecutive days. And sorry if I didn't mention this before and you can't see it, the y-axis is real power in kilowatts. Yeah, and so the top and bottom figure correspond to 2 kilowatt chargers. The on-arrival charging strategy with 100% of the electric vehicle fleet using chargers of the corresponding rating. So in the top case, all of our EVs are using the 2 kilowatt charger, and in the bottom one, all of our EVs are using the 4 kilowatt charger. Yeah, so it's less obvious to see here, but for those with a kind of finer tuned eye, you can see that with the 4 kilowatt charger, the EV load profile is slightly shorter in duration and slightly higher in magnitude. This effect is more profound with the delayed charging strategy due to the loss in load diversity. This can be seen here. So we can see here we've had a relatively significant reduction in the duration of charging, and that's coinciding with a considerable increase in the contribution to peak load. So yeah, from the distribution network's point of view, 4 kilowatt chargers as opposed to 2 kilowatt chargers have a negative effect, but of course this needs to be played off against the benefits for EV owners. It's probably important to note at this point that within this analysis, the load flow simulations were run alongside a parallel simulation of the EV batteries, and it was shown that for overnight charging at least, the 2 kilowatt charger was sufficient to ensure that EVs were fully charged the following morning in the vast majority of cases. Again, the graphs here show the probability of 1 or more voltage violations over the course of the week. The figure to the left is what we've seen previously, and the figure to the right here is the same information, but now for the EV fleet using the 4 kilowatt charger. We can see that with the 4 kilowatt charger, the voltage violation probability is higher across all charging strategies. Unlike with the 2 kilowatt charger, with the 4 kilowatt charger, the delayed charging strategy does not provide an improvement in performance at the higher penetration levels. This is due to that loss in diversity that we discussed previously. Okay, and finally, I'm going to give you a quick run over of range anxiety. Within this work, an anxiety factor was defined, and that is denoted as AF, seen here. And this is used to model an EV owner's tendency to charge. So simply put, an anxiety factor of 1 means that for any arrival state of charge, which is less than the battery's working capacity, the EV owner will charge to full that night, if possible. At the other end of the spectrum, an anxiety factor of 0 means that the EV owner will only charge if their arrival state of charge at night is less than that required for their journey the following day. Any intermediate values, for example, 0.5, describe varying degrees of anxiety regarding whether or not to charge. So if we start with the bottom, so if we start with the bottom profile here, which is an anxiety factor of 1, we've got the same information displayed as before. We've got 7 consecutive days. The blue profile is non-EV load, and the red profile is EV load. I've removed the different penetrations levels here just for ease of interpretation. So the EV contribution here is for the 100% penetration level. So yeah, in the bottom case, we have an anxiety factor of 1. All EV owners will charge their EV when they arrive home. And there's thus a relatively large contribution to peak load due to EVs. If we now contrast that with the anxiety factor of 0, here only the EV owners which have a state of charge less than what they require for their journey needs the following day will charge. And this has 2 ramifications. Firstly, the effective penetration level of EVs is reduced because only a subsample of the total EV fleet is charging each day. So we can see that the contribution to peak load is smaller with an anxiety factor of 0 compared to an anxiety factor of 1. Secondly, the charge duration is now increased. You can see that the charging tends to drag out a little bit longer, and that's because batteries are typically arriving home with a lower state of charge. So perhaps an anxiety factor of 0 is a little bit ambitious. So I've indicated an intermediate value there of 0.5. And again, it's probably worth noting that these results correspond to the 2 kilowatt charger and on arrival charging. Yep, okay, so finally let's look at the impact of range anxiety on the voltage violation probability. It can be seen that range anxiety has the potential to significantly reduce the voltage violation probability. In the most extreme case, the difference between, at the 100% penetration level, the difference between an anxiety factor of 1 and an anxiety factor of 0 is roughly a half. I guess at this point, it's also probably worth noting that the first 2 case studies I presented, so the impact of charger rating and the impact of charging strategy, they corresponded to an anxiety factor of 1. I just didn't want to introduce the terminology without fully describing it earlier in the presentation. Okay, so that is just about it from me. I figured I'd finish with a quick summary. So we've looked at some case studies on a typical residential network, and we've seen that whilst delayed charging often provides network benefits, when we have higher charger ratings, the loss in diversity can reduce this benefit. We have seen that the by morning strategy consistently provides the best performance, and that 2 kilowatt charges are most often sufficient to provide overnight charging needs. Finally, pessimistic assumptions regarding range anxiety may overestimate the impact of EVs during load flow simulations. Yeah, that's it for me. If you've got any questions, feel free to fire away. And thanks again to the to our sponsors of the Greenbird project. Thank you.
So I guess if anyone's got any questions for either Euan or myself.
Yeah, I have a question. Euan, if you're modeling this year, consider technologies available on chargers now in terms of delay charging, the possibility that they'll start manufacturing chargers where the EDB will control charge included, like some order city to take that manufacturing.
Yeah, sure. Just to reiterate the question to people who are listening online, as I understood it, have I considered charging strategies where a third party, be it the EDB or otherwise, are taking aggregated control of multiple EVs to provide network benefit? Yep, sure. Yeah, that is something I have looked at and have some results for. today, I guess we're kind of slightly constrained by time, so I didn't want to do more content and be firing through it at a kind of furious rate. But yeah, that is something that's already has been looked at, and hopefully I'll present those results in a different presentation at another time.
Brief summary.
Yeah, so I guess if you want a little bit more details on that, what I've looked at is a day-ahead optimization routine, which manages EV loads and LV networks in order to try and smooth out the aggregated load on the transformer, and that's the load due to EVs and non-EV load. So initial kind of results and findings from that is that having as your optimization objective function, trying to smooth out the transformer load without consideration of how you do that downstream of the transformer can actually have counterproductive results. So if you're not thinking about how the managing of that load affects diversity downstream of the transformer, whilst you can improve the transformer load profile, you might actually worsen voltages due to voltage imbalance and larger currents circulating through the neutrals. But as I said, there's quite a lot which went into that work, and I probably prefer to present that in its entirety on its own. But yeah, it's something we have looked at. So.
Question online for Euan. True. So he's asking for a meaning of 100% penetration.
Oh yeah, so I got a question from Nigel Purdy. Is 100% penetration equal to 1 EV per ICP on the LV network, or just the 17 you mentioned earlier? I guess that means just the 71 I mentioned earlier. So yeah, I'm only looking at one particular LV network. So 100% EV penetration means 100% local penetration in that LV network. So 100% means all 71 of those connections in that residential LV network have an EV. Hopefully that clears up the question.
From Kate. Yeah. And then we go to
Sure. We got a question from Kate here, which says, do you have any information on daytime charging as more businesses provide charging on site for employees? Yeah, that's something I definitely have considered, but haven't really put into action yet. I guess as I said, I do a simultaneous model of the EV batteries alongside the load flow simulation. So I guess where that would affect it, it's quite a simple simulation of the EV batteries. So they have the state of charge when they depart in the morning. I then pick a distance travelled, and that's a round trip distance, I guess, to their work and then back. And then I calculate the state of charge on arrival. So I guess there would be an extra stage added into that chain if an increasing percentage of workplaces had charging infrastructure. I guess the state of charge upon arrival could actually be higher than what it departed if there was charging infrastructure for them to charge their vehicles during the day. And of course, that's likely to be beneficial as network loading will probably be lower during the day. But as it's something I have thought about, but not really thought about how I could incorporate it into this work. Hopefully that clears that up, or it might have even made it worse. I'm not sure. Oh, we got a thanks, so that'll do. Sweet.
So have you considered if customers have more than one EV per customer?
Yeah. So I guess, that comes back. So sorry, the question was, have I thought about penetration levels? Well, actually, this is kind of essentially, have I thought about EV owners that might have more than one EV? There's kind of two ways that you can think about that, because the EV penetration level is the number of EVs divided by the number of connection points. And your 100% penetration level could actually be that only 80% of those connections have EVs. It just so happens that some of those which do have more than one. So it's I guess it's about how you interpret that penetration level that was previously discussed. Because depending on where as it comes back to depending on where the EVs are placed, that could be worse for the network or better for the network. If the EV owner that's went EV daft and got 5 EVs is located right close to the transformer, it's not as much of a problem as if he's far away. So it plays back in with the probabilistic simulation framework.
Sort of following off that note, if you looked at any mitigation against suburbs having different levels of penetration, that is large penetration and larger problems versus just problems on 400 volt.
Oh, sorry, what was the kind of second part of that question?
So you're looking like a 400 volt network.
Yep.
As one isolated point, but if you have different suburbs and different penetration levels, does that cause a problem?
Oh, okay. So correct me if I'm wrong, just to repeat the question back. Have I looked at, rather than looking at individual LV networks in isolation, looking at how individual LV networks aggregate into the medium voltage network and how it's likely that certain LV networks in affluent areas are likely to have higher penetration levels, and how when aggregated that will impact the MV. Correct? Okay, sweet. In short, no. But I guess, all those things are interlinked. And I guess maybe someone in the research group will be looking at it, but my primary focus as part of my PhD has just been LV networks. But I'm sure it's something that will definitely be in the scope for future work.
Is it fair to say that you established certain principles that we extended and applied in EPECentre?
Yeah.
That's a fair response to that?
Yes. Cool.
So there's
So
another
two
question
more, Two more
online.
questions. Yeah. Is modeling of combined PV and EV chargings? And do you have a similar product? Or maybe you can tell us too.
Okay, so one of the questions online is, do you have similar product as DGHost for EV hosting? And to date, no. We're sort of looking towards what we'd have to do and what you'd have to implement to do that. But that is something we're looking at doing. As I sort of alluded to, there's a bigger parameter space to explore, but that would be very helpful. And yes, it has been also mooted. There's another question. Is modelling of combined PV and EV charging being undertaken or planned? That's another step further, and ideally that would be nice, but not in the near future. But it's something we have thought about, but it's quite a big problem to solve because the parameter space just gets enormous.
Maybe I could add something slightly to that. Just about the kind of framework through which those results are generated. I guess maybe it's worth noting that quite often when you do load flow simulations, you're focusing at one particular snapshot in time. Maybe say take the maximum demand indication from the transformer, or some assumption that our peak load is usually at 7 o'clock at night. It was a kind of conscious decision that was made at the start to have a temporal element to the simulation. So you saw there that 7 consecutive days were modelled in time, and that would allow the simulation framework to simultaneously look at EV and PV, because if you're honing in on just 7 o'clock at night, then that's probably good for looking at electric vehicles. But if you're honing in at 12 o'clock, mid-polar element allows you to look at the impacts of both simultaneously, if that makes sense. Yeah.
So you have taken the 7 days.
Yeah.
So does it be different if you take a different 7 days of different year? Or in the same year, you take a summer 7 days and winter 7 days? The question there was, my simulation was ran for 7 days, and those were a particular 7 days. What sort of impact would it be if I picked a different 7 days? Sweet. So when modelling the electric vehicles, there's no dependence in my model of time of year. Perhaps there is a dependence. Perhaps people drive more in the winter than they do in the summer, but I don't have that information, so my model just has to assume that at this stage that there's no dependence in my people drive with the time of the year. On the other hand, for the non-EV load that I have in the smart meter data set, that varies considerably throughout the year. And the particular week that I picked was the week which had the peak load in the data set I use. So it will give you an indication of the time of year that transformer loading, network currents and network voltages are likely to be at their most extreme. You could also look at sometime during the summer, perhaps, for looking at PV. Or you could do the whole year. There's essentially a trade-off between computation time and the amount of information that you can kind of glean from the results. Does that make sense? Cool.
See, just another thing to add about the PV and EV combination is that often when you've got both, you're not striking the same, they're not acting against each other, because normally when your PV is high as in the summer and the midday, and which is typically not a time when you're charging, which is in some ways why it doesn't offset each other. So you have, so in some ways it's almost valid to consider them separately, because you're really concerned about EV charging when you've got your high load times, which are typically winter at sort of the evening peak. So you're actually, you can consider them separately, but I guess the issue is that if you're an EDB, an electricity distribution business, sometimes you change your buck boost of your transformer. You either put it up, your voltage up if you think you've got high loads, or you put it down if you've got lots of PV. The problem is that generally these are statically set, they're not online changes. So if you want to be able to solve the problem for both, it's quite hard, and they're happening at different times, so they're not overlapping that much. Batteries.
Yeah.
There's another question online from Edward Pilbrow. Do you have any graphs of the uptake rate of house scale residential batteries? These should help with high uptake of both PV and EV. And yes, well, yes, they will help with PV and EV. Unfortunately, we don't have that data is not available nationally, so we don't, but there is talk about the Electricity Authority, there is talk about trying to add batteries, so we know what's happening with batteries. We know just by anecdotally that the number of batteries are increasing, but we don't have hard figures for that at the moment, but that's something that's planned to be added.
What do you grid help offset the change in voltage in relation from vehicles to photovoltaics? Because when there's a B and E thing, when photovoltaics is slow, but there's still a rush of
well, with electric vehicles, if you look at a typical scenario where people work away from the home, often the electric vehicle's not at home when your PV's at its maximum generation. So yes, it will help, but it's probably not the silver bullet, because it will work for some households, people that work from home, or maybe they always leave an EV sitting in the garage and only use it occasionally. But yeah, it helps to some degree, but it's not clear how much. And we don't really have vehicle to grid at this stage. It's a very new thing, but so yeah, it'll be interesting to see what happens there. But it's a kind of, the timing's not quite right for the typical scenario for people that go out to work. But yeah, it's just essentially connect like a battery. So. No, I think that's it for questions online. So wrap it up.
Yeah.
Oh, I'd just like to thank you all for coming, and yep, hope you found out something interesting or useful. Okay. Thanks very much.